So we've got these two equations. Change in entropy for the universe is equal to the system plus the surroundings. And the change in entropy for the surroundings is equal to negative delta H for the system divided by the temperature. So let's put these two equations together. So how might we do that? Well, delta S surroundings equals this, so we could substitute this in for that. So I'm going to take this guy and plug it in over here. So I'm going to get delta S universe is equal to change in entropy for the system. And then this is a negative. I'll just do it like this. Plus negative delta H cis over T. Okay with that? Let's multiply both sides by negative T. So if I do that, then I'm going to end up with negative T delta S of the universe is equal to, I hope you don't mind, I'm going to switch the order of these. When I multiply this one by negative T, what do I have? Positive, just delta H, right? And then when I multiply this one by negative T, I get negative T delta S for the system. So multiplied by negative T. So the signs on all of these change. So this becomes negative, this is negative, this one's positive now. And I got this delta T, I got that T went away, but now I added T's over here, and there's a reason for that. Yeah?
We're going to need all 7 of those equations for, say,
Are you going to need all 7 of those equations?
because they're very similar.
They're very similar. We'll talk about that later. So we've got all these subscripts, right? So what we've got over here is we've got system and system. And so we're just going to drop that. Just going to drop that. And just understand that if there's no subscript, that's referring to the system, the part of the universe we're interested in. And over here, this is the change in entropy for the universe. So we're going to bring in a new quantity, and it's called the Gibbs free energy. And it has the symbol G, which is kind of nice because Gibbs starts with G, unlike enthalpy, which doesn't start with H, and entropy doesn't start with S. I mean, how is all of that? So G is nice. I like G. Gibbs free energy. The Gibbs free energy is equal to enthalpy minus the temperature times the entropy. So temperature in kelvins, right? And so the change in the Gibbs free energy is delta H minus T delta S at constant temperature. So choose a pen. The change in that is equal to the change in the enthalpy. Now we would put delta T, delta S, except we specify constant temperature. So then there's no change in the temperature. Delta G equals delta H minus T delta S. So the change in the Gibbs free energy, delta G, for a process occurring at constant temperature and pressure is proportional to the negative of delta S. So where did I get that from? Negative T delta S for the universe equals delta H minus T delta S. this is equal to delta G. Whoops. Okay, so delta G equals negative T delta S of the universe, or for the system, delta H minus T delta S. It's going, what? Well, we said that in order for a process to be spontaneous, the change in entropy for the universe has to be positive, right? The entropy has to go up. It can't go down for the whole universe. So we have a negative sign in here. If the change in entropy for the universe is positive, then the change in the Gibbs free energy is negative. Because Gibbs free energy is proportional to the entropy change for the universe, we can also use delta G to measure spontaneity. Okay with that? So Gibbs free energy is also called chemical potential energy. It's analogous to mechanical potential energy. You know, holding something up above the ground or pushing something down into a spring, right? It's a mechanical potential energy. But this is a chemical potential energy. So we find that chemical systems tend towards lower Gibbs free energy. When delta G is less than 0, we have a spontaneous process. Because when that occurs, the entropy change for the universe is positive. Yes?
So the negative's built in with a T delta entropy for the universe, right?
Mm-hmm.
So if it's a negative temperature, wouldn't that offset that negative?
That's a good question. What if the temperature was negative? What are the units on the temperature? Kelvins. Can't have a negative Kelvin temperature. Which is why we're using kelvins, because that would be a problem, right, if you had negative temperatures. Good question. Anybody else? So here's an energy diagram. Free energy, the Gibbs free energy, and reaction progress, I suppose you could say. So here you've got nitrogen and hydrogen. Here you have an equilibrium mixture, and over here you have pure ammonia. And what will naturally happen is this reaction will end up at an equilibrium, which corresponds to the lowest Gibbs free energy for that system. If you go over here, that's going to increase the energy. If you go to the left, that's going to increase the energy. And so like a ball rolling down a hill, if this was a little valley and we were rolling a ball, it would come down and settle at the bottom because that's the lowest potential energy, right? So it will settle at the lowest chemical potential energy. We can calculate delta G just in reference to the system. We do not have to involve the universe, so that's convenient because the universe is kind of big to deal with. We learned how to calculate delta H back in Chapter 6 in Chem 1A, and we've just looked at how do you calculate delta S. Right? So delta G equals delta H minus T delta S. What effect do delta H, delta S, and T have on spontaneity? And so we're going to look at 4 different scenarios. The first one, we've got delta H being negative and delta S being positive. And so even without understanding what Gibbs free energy is, delta H negative is an exothermic process, right? Those tend to be spontaneous, and the change in entropy for the system is positive, right? We're subtracting the change in entropy for the system. And we know that when the entropy increases, that promotes spontaneity as well. So here we have a negative delta H. We're subtracting a positive number here. And so at all temperatures, this is going to be negative and spontaneous. That makes sense? We could look at this reaction at the bottom here. The heat of reaction is negative, so there's our delta H. We can look at the moles of gases present, 2 moles of gases going to 3 moles of gases. When this reaction occurs in the forward direction, the entropy increases. And the combination of those at any temperature will be a negative Gibbs free energy, spontaneous reaction. Any questions? What if delta H is positive and delta S is negative? We've got an endothermic reaction, and the entropy is actually going down. So we've got a positive delta H and a negative delta S. We're subtracting that, and so this can only give us a positive result, right? And so this will be positive at all temperatures. There's no temperature at which this is going to be spontaneous. So an example of this is, there's got to be a typo in that one, huh? I'm pretty sure that's supposed to be ozone. That would be a non-spontaneous process, though. Oxygen going to nitrogen. Okay. So here we're going from 3 particles to 2 particles, so that's concentrating. That's a negative entropy, not good for spontaneity. And we've got delta H being positive, also not great. Delta H is negative and delta S is negative. So exothermic reaction, but the change in entropy is negative. It's becoming more ordered. Well, here, temperature is going to have an effect because temperature multiplies the effect of entropy. So at high temperatures, this negative change in entropy is going to be more significant than at lower temperatures. We get down to 0 Kelvin, this term goes away, and we're just looking at delta H. So delta H is negative. That's going to give us a negative delta G unless this is adding too much. So it'll be spontaneous at low temperatures and non-spontaneous at high temperatures. Example of this is liquid water. Liquid water going to solid water, so water freezing. Exothermic process, but negative change in entropy. Happens at low temperatures, not at high temperatures. Any questions? What if they're both positive? So we've got positive delta H, positive delta S. So this one's promoting spontaneity, this one is opposing it. Now, at higher temperatures, we're going to be more spontaneous, and at low temperatures, it will be less spontaneous. So here we've got liquid water going to gaseous water. This is an endothermic process. And so this will happen more easily at high temperatures than at low temperatures. Any questions? So when delta H and delta S have the same sign, whether it's spontaneous or not will depend on the temperature. The temperature at which it goes from spontaneous to non-spontaneous can be found by setting delta G equal to 0 and solving for T. Because if delta G is 0, that's that tipping point between spontaneous and non-spontaneous. And then this is a summary of the 4 situations we looked at. If delta S and delta G have different signs or the same sign, and what does that mean for the reaction being spontaneous or not? So consider this reaction. And we're given delta H and delta S. Calculate delta G at 25 degrees Celsius. Determine whether the reaction is spontaneous. Does delta G become more negative or more positive as the temperature increases? Well, what's the equation for delta G? Delta H minus T delta S. So delta G equals delta H minus T delta S. So we've got delta H and we've got delta S. We need to watch our units because this is in kilojoules and that one's in joules. So this is going to be delta H minus 137.5. I'm just going to put that into joules by writing 10 to the third instead of kilo. So there's delta H minus temperature in Kelvin, so 298.15 Kelvin, times the entropy change, minus 120.5 joules per Kelvin. I'm getting a really big number, which makes me think, gosh, should have stayed with kilojoules, right? Negative 101,572.925. Might as well just write them all down. And the unit there, because the kelvins cancel, the unit is joules. So it might be nice to put that into kilojoules. So minus 101.6 kilojoules. Is it spontaneous?
Yes.
Yes. Delta G is negative, is spontaneous. Is it going to become more negative or more positive as temperature increases? So as this temperature gets larger, I'm subtracting a negative number. I'm adding, right? And as temperature increases, I'm adding a larger and larger number. So it's going to become more positive, right? And we'll get to some point where this stops being spontaneous when delta G becomes 0 and starts to become positive. Any questions?